Alright, time to get into the interesting practical stuff, even more practical than we've been doing so far. So we've defined a bunch of things so far in terms of electricity. Now we're going to start talking about how you can use those to make circuits. So here we go. First we're going to start with series circuits, and we're going to talk about several different factors in a series circuit that are just true. Several different things that are true about series circuits. All right, in terms of current, potential difference, the effect of combining different EMF sources in series, and so on. So, what is a series circuit? Well, let's define it. The current must flow through all of the loads in the circuit, or all of the components, or possibly we might be talking about a branch of a circuit, a certain portion of a circuit that is in series, where maybe other parts are not in series. But in any case, this is an extremely simple circuit that, as with many examples, is totally impractical for any use that you would actually use, because these are just resistors. They wouldn't do anything by themselves. But this sort of circuit serves to illustrate what we're talking about. All right. This represents electrochemical cells, these symbols. That would be two of them. The symbol for an electrochemical cell is a long line and a short line. And basically you would call that a battery. More accurately, this would be a cell, an electrochemical cell. And then if you put more than one of those together, like this, that's called a battery. So a battery is technically only multiple electrochemical cells combined together. So otherwise it's just a cell. All right. Alright, so let's talk about current in a series circuit. In a series circuit, the current is the same at every point in the circuit. This is all the same pathway, so there has to be the same amount of current flowing at all points, because the current leaves the power supply and the current comes back to the power supply. The current leaving has to equal the current coming back, and current is not used in a circuit. Energy is used, the current is not used. So the current just flows, it's not used up. The same amount of current that leaves is the same amount of current that comes back. Now energy, of course, the energy that leaves the power source is used up by the circuit, and when the current comes back again, it's used up its energy. This is a weird concept, but that's how it works. Current is not used up, potential difference is not used up, only energy is actually used up by the components in the circuit. Right. So the current is the same at every point. In this circuit, again, same current at all points in this own circuit. Now the current is not the same from one circuit to another, right? This is a different circuit from this one. Now these little lines that I drew here are supposed to indicate the brightness of this lamp. That's incidentally, this is the symbol for a lamp. The circle with the X through it, that is the symbol for a lamp. All right. So what we have here is, in this circuit, same power supply, two cells together, so we'd call that probably 3 volts of power. All right. And then there's 3 lamps here. In this part, 3 lamps, 1 lamp here. Let me just identify that really quick. Lamp. Alright, so 3 lamps versus 1. Now what you should notice is that I drew these as being dimmer, fewer little lines coming out. So what's going on? Well, as you add more components into the circuit, you increase the resistance of the circuit, and that decreases the current. We'll talk about that in a second. But if you add more stuff into the circuit, generally you're going to decrease the current compared to this one, right? So this circuit would have less current than this circuit, and therefore the lamp here glows brighter than this lamp. All right. So let's talk a little bit about potential difference. In a series circuit, the potential difference gets split up across all of the loads. So you've got a certain amount of potential difference here. Again, let's just say that it's 3 volts, all right? And then we've got 3 circuit components that we'll just say, for the sake of simplicity, we'll say these are all identical resistors. They're all resistors, and we'll say that they're all the same. So that would mean that the potential difference would get split evenly across them, and this one would get 1 volt, this one would get 1 volt, and this one would get 1 volt. So that the sum of the potential differences, the sum of all the potential differences of the components is equal to the total potential difference of the power supply. All right? So this guy plus this guy plus this guy equals this guy. All right, so the EMF of the power source is equal to the potential difference combined for all of the components in the series circuit. So that is how that works for potential difference. So what about the total resistance? I mean, how do you combine the resistances in a series circuit? Well, basically, this is going to be pretty intuitive. They're all in a row. So if you want to find the total resistance in the circuit, then basically you just add them up. Take this resistance plus that one, add them up, bam, that gives you the total resistance. And that's it. It's that simple. So total resistance is equal to the sum of the individual resistances in the circuit. It is not this simple when we talk about parallel circuits, but for a series circuit, pretty straightforward. All right, and the last thing for this video, we want to talk about EMF, sources of EMF. So here what I've drawn, or what I've got a picture of right there, is the back of a calculator. And you'll see there are 4 AA batteries in there. And then I've drawn what you might picture that as if it was a circuit symbol diagram. Each battery is 1.5 volts. And here's the thing, if you put EMF sources in series with each other, their EMFs add up with each other. So you got 1.5 times 4 all in series, then their EMFs all add up, and you get a total of 6 volts, which is 1.5 times 4. You might be thinking to yourself, and if you think back to this picture, once we talk about parallel circuits, you would think, wait a minute, those are in parallel. They're not in series. They're not in a line with each other. They're not all lined up like you think of stacking them, one here, one there, all in a line with each other. They're not. They're next to each other. But here's the thing. They're alternating. You see how they alternate which side they're on? You can't see this going on behind the picture here, but this is the plus side of a battery, and this is the minus side. So let's follow, right? Here's plus, here's minus. So if these are in series, you should see a minus connected to a plus, minus connected to a plus, all the way down till you end with a minus. So you start with a plus and end with a minus. Now watch this, all right? The way the circuit actually works, you've got a start of the circuit right there. It goes through this battery, and then it goes through a metal piece that you can't see back there. And then it goes through this one this way, and then a metal piece back there, through this one this way, metal piece back there, through this one this way. Bam. So you've got the start over here, and you've got the end over here, and it flows through like that. Bam. Start to end. Dude! Who knew? Anyway, so that's the topics for this video. That's a lot to know about series circuits, but let's just review really quick. We talked about current, potential difference, total resistance in the circuit, and then putting EMF sources in series and how that works as well. So that's a lot, and there's a lot of important concepts in there that we'll work with more as we do some problems, but for now, that's all I've got for you. Thanks for watching, and I'll catch you next time.